All right, hey everyone, welcome. So today we are going to tackle this huge mystery, basically the universe's superglue. We're talking about the fundamental forces that hold literally everything together, chemical bonds.
I mean, have you ever really stopped to think about it? Why is the salt in your shaker a tiny crystal and not like a puff of gas? Why is water a liquid? These aren't just random trivia questions. They're some of the biggest puzzles in chemistry, and today we're going to solve them. And the answer to all of it actually boils down to one simple, super powerful idea that drives every single atomic interaction: the search for stability. You can think of it like this: every bond, every reaction, it's all just an atom trying to get to its happy place. Okay, so let's get into it. I want you to picture the periodic table as this giant high school, right? All the way over on the far right, you've got the noble gases. These guys, they are the cool kids. They're totally stable, perfectly content, because their outer shell of electrons is completely full. They don't need to bond with anyone. Every other atom in that school, they want to be just like them. And that right there, that's the main idea. Atoms form chemical bonds to complete their outer energy levels and become more stable. That one sentence, that's the why behind pretty much all of chemistry. It's their motivation for everything. So how do they get to be like those cool kids? Well, that brings us to the number one rule of their little social club, the octet rule. The octet rule is actually pretty simple. It just means atoms will do pretty much anything to get a complete outer energy level. And for most of them, that magic number is 8. 8 valence electrons. That's the goal. That's like atomic enlightenment. Now, to hit that magic number 8, atoms have kind of 3 main strategies. They can give and take electrons. That's an ionic bond. They can share electrons. We call that a covalent bond. Or for metals, they kind of create this big sea of shared electrons in what's called a metallic bond. We'll get to all of them for sure, but today, we're diving into the drama of the give and take, ionic bonds. All right, so ionic bonds. You can think of these as the ultimate you scratch my back, I'll scratch yours relationship in the atomic world. It's a story about 2 very different kinds of atoms getting together, where each one gets exactly what it's looking for. Okay, so once this electron trade happens, what's the glue holding them together? It's a force we call electrostatic attraction. Now, that sounds fancy, but it's really just the most basic rule in all of physics. Opposites attract. A positive thing is drawn to a negative thing. Simple as that. So this lays out our 2 main players perfectly. On one side, you've got the metals. Think of them as the givers. They only have a few electrons in their outer shells, so it's way, way easier for them to just get rid of those few and reveal a nice full shell underneath. And when they lose those negative electrons, they become positively charged ions, which we call cations. Then on the other side, you have the nonmetals. These are the takers. They are so close to having a full shell, they just need to snatch 1 or 2 more. When they gain those negative electrons, they become negative ions or anions. Okay, let's see this in action with the most famous ionic couple out there. So meet sodium, Na. It's a metal, and it's got just 1 lonely electron in its outer shell. And then we've got chlorine, Cl, a nonmetal with 7 valence electrons. It is desperately looking for just 1 more to complete its set. So here's how the whole thing goes down. Step 1. Sodium donates its 1 valence electron. Bam, it's now a happy +1 cation. Step 2, chlorine eagerly snaps that electron up, completing its octet and becoming a -1 anion. So now you have a positive ion and a negative ion. What's going to happen? That's right, electrostatic attraction pulls them together like magnets. And the result? NaCl. Yep, table salt. A perfectly stable neutral compound where everybody is happy. Okay, so that was a nice, clean, 1-for-1 trade. But what happens when the math isn't quite so simple? This brings us to building some more complex ionic compounds, where the whole game is about balance. So, here's the next little puzzle for you. What if one atom wants to give away more electrons than the other atom wants to take? Let's look at magnesium and chlorine. Magnesium is in group 2 of the periodic table, which means it has 2 valence electrons it really wants to get rid of. When it does that, it'll have a +2 charge. But our old friend chlorine, well, it only has room for 1 more electron, which gives it a -1 charge. You see the issue here? Magnesium has 2 electrons to give, but a single chlorine can only take 1. The solution here is actually pretty elegant. If 1 chlorine isn't enough to help magnesium out, you just bring in another one. Magnesium just bonds with 2 chlorine atoms, and suddenly everything works out perfectly.
And that gives us our final formula, MgCl2. So magnesium gives one electron to the first chlorine, and its second electron goes to the second chlorine. Now, magnesium is a happy +2 cation, and you have two -1 anions. That +2 charge is perfectly balanced by the two -1 charges. The final compound is stable, and, this is key, it's neutral.
So, now that we know how they're built, what's life actually like for these ionic compounds? Well, their whole bonding style leads to a pretty distinct lifestyle. It's strong, it's superstructured, and, you probably guessed it, it's usually pretty salty. That electrostatic attraction is ridiculously strong, which gives these compounds some really specific properties. For one, they have crazy high melting and boiling points. You need a ton of energy to pull those ions apart. They form these hard, brittle solids in a really organized, repeating 3D pattern called a crystal lattice. And yeah, as a general rule, we just call all these things salts. So, if there's one single rule you need to remember for any stable ionic compound, what is it? Its overall charge is always 0, period. The positives and the negatives have to perfectly cancel each other out, no exceptions. But check this out, here's one last cool thing they do. What happens when you drop something like salt into water? The water molecules are actually powerful enough to get in there, surround the ions, and literally pull that ionic bond apart. We call this process dissociation. And all of a sudden, you've got these positive sodium ions and negative chloride ions just floating around freely. And because you have charged particles that can move, that solution can now conduct electricity, which, by the way, is exactly why you don't take a toaster in the bath with you.
So we've seen the incredible strength that comes from this whole atomic give and take. But that leaves us with a really interesting final question. If this is what happens when atoms transfer electrons, what in the world happens when they decide to share them instead?